Let's break down the core idea behind this paper. KIVI, a tuning-free asymmetric 2-bit quantization for the KIVI cache, from Rice University and collaborators. It's a beautifully simple trick for shrinking the biggest hidden cost in serving large language models, and you don't have to retrain anything to use it. Here's a cost almost nobody talks about. When a large language model generates text, it keeps a running scratchpad called the KIVI cache, and that cache can quietly grow bigger than the model itself. For a big model serving many users at long context, it can balloon past a terabyte of GPU memory, several times the size of the model's own weights. It's the real bottleneck in serving, in both memory and speed. KIVI squeezes that cache down to just 2 bits per number, cutting peak memory by about 2.6 times, letting you run up to 4 times the batch size, and boosting throughput by 2 to 3.5 times, with almost no loss in quality and no retraining at all. Let's see how it works. First, what is the KIVI cache, and why does it even exist? Attention works by having each new token look back at every previous token, comparing against a key and pulling from a value for every token that came before it. Recomputing all of those keys and values from scratch at every step would be insanely wasteful. So the model computes each token's key and value once and caches them. Every new token then just appends its own key and value to the cache and reads the whole thing back. It's a pure speed optimization, and it works. The catch is that the cache grows with every token, and it grows once per layer, and once per attention head, and once per item in your batch. Those multipliers are about to bite. Let's make the size real. Take a very large model serving a big batch of long prompts. The KIVI cache holds a key and a value for every token, every layer, every head, and every request in the batch, and the numbers explode. For one large model, that's over a terabyte of cache, several times the size of the model's own weights. And it's not only a memory problem, it's a speed problem. To generate each single token, the GPU has to haul the entire KIVI cache out of its main memory into the fast on-chip memory. And while that transfer is happening, the compute cores mostly sit idle, just waiting. The model isn't compute-bound, it's memory-bound, starved by the sheer size of the cache. Shrink the cache, and you fix both problems at once. The paper puts the scale of the problem starkly. People have attacked this before in 3 broad ways. 1. Use fewer key-value heads, sharing them across query heads, which is what multi-query and group query attention do. But that changes the architecture, so you have to train or fine-tune the model for it. 2. Evict tokens. Just throw away the ones you guess don't matter, which risks dropping something you actually needed. 3. System tricks. Offload the cache to CPU memory or page it like virtual memory. KIVI takes the simplest path of all. Keep every token, keep every head, and just store each number in fewer bits. Quantization. The whole game is doing that without wrecking accuracy. So let's be precise about what quantizing the cache means. Each number gets mapped from a full 16-bit float down to a tiny integer, in KIVI's case a 2-bit integer, which has only 4 possible values. You take a group of numbers, find their minimum and their maximum, and stretch that range across your 4 levels. Subtract them in, divide by a step size, round to the nearest. To recover an approximate original later, you multiply back and add them in. 2 little bookkeeping numbers, a 0 point and a scale, per group. It's called round to nearest quantization, and it's simple and streaming friendly, which matters, because the cache arrives 1 token at a time, and you can't afford a heavy offline optimization for each new token. Now, the crucial question the whole paper turns on. When you group numbers together to quantize them, which numbers do you group? The KIVI cache is a grid, tokens along one axis, and channels, the feature dimensions, along the other. You have 2 natural choices. Per token quantization groups all the channels of a single token and quantizes them together. Per channel quantization goes the other way, grouping the same channel across many tokens. It sounds like a minor implementation detail. It absolutely is not. This one choice is the entire difference between 2-bit quantization that works and 2-bit quantization that completely falls apart. Here's the evidence that it matters. The default, easy choice everyone reaches for is per token, for both key and value, because it fits the streaming pattern so nicely. At 4 bits, that's totally fine, accuracy holds. But drop to 2 bits with per token everything, and accuracy falls off a cliff, a task score crashing from 66 down to 53. 2 bits is exactly where the naive approach breaks. So the authors did something that sounds obvious, but is usually skipped. They actually looked carefully at what the numbers inside the key and value caches actually look like. And they found that the two caches are not the same at all. This is the key observation, and it's worth staring at. If you plot the magnitudes in the key cache, you see something striking. A few specific channels, always the same ones, have enormous values, towering outliers, while every other channel is small and well-behaved. These persistent outlier channels are a known feature of transformer activations. Now look at the value cache. No such pattern at all. The values are smooth. No single channel consistently blows up. Two caches, two completely different personalities. And that difference is exactly why they need to be quantized in two different directions. Take the key cache first. It has those violent outlier channels. What happens if you quantize it per token, grouping all channels of a token together? That group now contains both a giant outlier channel and a bunch of tiny normal channels. The outlier stretches the min-to-max range enormously, so your 4 measly levels get spread across a huge span, and all the normal channels collapse into basically one level, their information destroyed. The fix is to quantize the key cache per channel. Group each channel with itself across tokens. Now the outlier channel is isolated, its errors stay contained inside its own group, and the well-behaved channels get quantized cleanly on their own tight range. Per channel confines the damage. In fact, per token here gives about 5 times the attention score error that per channel does. The value cache is the mirror image, and it's more subtle because it has no outliers, so you'd think the grouping wouldn't matter. It does, and here's why. The value cache doesn't get compared like keys do. It gets mixed. The attention output is a weighted sum of value vectors across tokens, and crucially, attention is sparse. For any given output, only a few tokens actually receive meaningful weight. If you quantize per channel, an error in one channel smears across all tokens, including those few important ones, and pollutes the output. Quantize per token instead, and each token's error is sealed inside that token, so quantizing the many unimportant tokens simply doesn't touch the important ones. The per token error here is about 15 times smaller. Value once per token. Put the two insights together and you get KIVI's signature move. Quantize the key cache per channel and the value cache per token. An asymmetric scheme, different directions for the two caches. And the ablation is decisive. At 2 bits, per channel keys with per token values scores 63.5, nearly matching the 16-bit baseline of 66. Every other combination is a disaster. The two symmetric options, and the flipped one crater to single digits, or worse. There's really only one right answer, and the distribution analysis is what pointed straight at it. The recipe, stated plainly in the abstract. But there's a serious catch hiding inside that clean recipe. Per token value quantization is easy in streaming. A new token shows up, you quantize its values, append them to the cache, done. But per channel key quantization needs a whole group of tokens along the channel direction before you can even compute that channel's min and max, and tokens arrive one at a time. You literally cannot quantize per channel until you've accumulated enough tokens. The very thing that makes the key cache quantize well is what makes it awkward to implement in a live, token-by-token generation loop. So KIVI needs a data structure to bridge that gap. Here's their solution, and it's clever and practical. Split the key cache into 2 parts. The grouped part holds full, complete groups of tokens, enough to quantize per channel properly, and those get compressed down to 2 bits. The residual part holds the most recent handful of tokens, the ones that haven't yet accumulated into a full group, and those are kept in full precision. As generation proceeds, new tokens land in the residual part. Once it fills up to a set size, that chunk gets quantized and folded into the grouped part, and the residual resets to empty. The value cache gets the same treatment. And because the residual is capped at a small number of tokens, its memory cost is negligible next to the huge savings from 2-bit compression. How do you compute attention when your cache is half 2-bit and half full precision? You split the math to match. The attention scores against the grouped, quantized part are computed in a fused, mixed precision matrix multiply, one that dequantizes on the fly, right at the hardware tiling level, so there's no separate, expensive unpacking step beforehand. The scores against the small full precision residual are computed the normal way. Then you simply concatenate the two sets of scores, and attention proceeds exactly as usual. The quantized bulk and the full precision recent window get stitched back together seamlessly, and the whole thing is written as efficient custom GPU kernels. That residual part turns out to have a lovely side benefit. Because it always holds the most recent tokens in full precision, KIVI effectively maintains a sliding window of the newest tokens at full quality, and only the older history gets compressed to 2 bits. And it turns out the most recent tokens are exactly the ones that matter most for hard, reasoning-heavy tasks. On something like grade school math, where the model needs precise access to the numbers it just wrote a moment ago, keeping that recent window in full precision is what rescues the accuracy. It's a small design choice that quietly does a lot of work. Quick pause. If squeezing a language model's memory down to 2 bits, without retraining it, is the kind of clever but practical trick you enjoy, then you know the drill. Like, subscribe, and share it with someone who's currently fighting their GPU bill. It really does help. Alright, let's look at what it actually buys you. One thing worth underlining. KIVI is tuning-free and plug-and-play. There's no fine-tuning, no retraining, no calibration dataset. You take an existing model, wrap its KV cache with KIVI, and it just runs. The authors also put real engineering into making it fast, fusing the dequantization directly into the attention matrix multiplication and writing dedicated group-wise quantization kernels, so that the savings in memory don't get quietly eaten back up by overhead. That combination, a big memory win, tiny compute overhead, and zero model changes, is exactly what makes it something you'd actually deploy in production. So what does it deliver? Start with memory. On a standard 7 billion parameter model, KIVI cuts peak memory usage by about 2.6 times, and that's counting the model weights too, not just the cache. The cache itself, the part KIVI actually compresses, shrinks far more than that, from 16 bits per number down to 2. And because that full precision residual window is so tiny, it barely dents the savings. Suddenly the thing that was several times bigger than your model becomes just a small fraction of what it used to be. And memory converts directly into speed through batch size. The reason serving is memory-bound is that the KV cache eats all your GPU memory, leaving no room to process more requests at once. Free up that memory, and you can pack in up to 4 times as many requests per batch. More requests sharing the same expensive weight loading means far better hardware utilization, and the measured result is 2.3 to 3.5 times higher throughput on real inference workloads. You're serving 3 times the traffic on the very same GPU. That's the payoff. The headline numbers, straight from the abstract. The obvious worry with 2-bit anything is that quality quietly tanks. It doesn't. Across a range of models, Llama, Mistral, Falcon, and a spread of generation tasks, KIVI holds accuracy essentially even with the full precision baseline. Little to no measurable drop. And that is the entire point of doing the distribution analysis instead of just crushing everything to 2 bits. By quantizing each cache along the direction that fits its structure and keeping a small full precision window of recent tokens, KIVI spends its 2 bits where they can afford to be spent and protects what actually matters. It's worth seeing that the full precision residual window isn't optional decoration, it's genuinely load-bearing. When the authors test on hard tasks, the ones that require the model to hold precise recent context, like multi-step arithmetic, removing that recent full precision window causes a real accuracy drop. The lesson is subtle. 2 bits is perfectly fine for the vast bulk of the cache, the older tokens, but the freshest tokens carry disproportionate weight and deserve full precision. Getting that split right is a big part of why KIVI keeps quality exactly where cruder 2-bit schemes lose it. In fairness, the trade-offs. The residual window and the grouped structure add real implementation complexity. This is not a 2-line change, it's custom CUDA kernels. The whole approach leans on an empirical fact that key caches have fixed outlier channels and value caches don't. which holds for today's transformers, but isn't guaranteed for every future architecture. 2 bits is aggressive, and on the very hardest tasks, there can still be a small residual gap. And you do carry that little full precision window, negligible, but not literally zero. Sensible costs, though, for turning a terabyte of cache into a few hundred gigabytes. Zoom out. KIVI is part of a broader realization that as context windows stretch to hundreds of thousands of tokens and serving scales to enormous batches, the KIVI cache, not the model weights, is the thing you increasingly have to engineer around. Its core lesson has stuck. The key and value caches are structurally different objects and deserve different treatment. Keys have outlier channels, values are mixers, and the sparsity of attention is something you can actively exploit. KIVI cache quantization is now a standard tool in the long context serving toolbox, and the asymmetric per channel, per token idea shows up well beyond just this one paper. Let's put it back together in one breath. The KIVI cache is the hidden memory and speed bottleneck of LLM serving. Look at the numbers inside it. Keys have fixed outlier channels, so quantize keys per channel to contain them. Values are a sparse mixer, so quantize values per token to isolate them. To make per-channel keys work in a streaming loop, split the cache into a 2-bit grouped part and a small full-precision residual window of recent tokens and stitch them back together with a fused mixed-precision matmul. The result, 2 bits per number, 2.6 times less memory, up to 4 times the batch, 3 times the throughput, the same quality, and no retraining. That, end-to-end, is KIVI. Here's the thought I'll leave you with. KIVI works because it noticed that keys and values, which we usually treat as an interchangeable pair, are actually different kinds of objects with different statistics, and that attention is sparse enough to hide a lot of error. Which makes you wonder how many other places in these models we're applying one uniform treatment to things that quietly want to be handled differently. Where else is there structure we're averaging over, simply because nobody bothered to look? That's my read. Tell me yours.